Okay, good morning. So, have you been here last session as well? Okay, so if you remember, let me just tell you, if you have a triangle here, ABC. So we know that for every triangle, we can talk about angle bisectors. We can talk about the altitudes. We can talk about perpendicular bisectors, and we can also talk about medians. So for angle bisectors, for perpendicular bisectors of the sides, and for the altitudes, we proved that they are all concurrent. So it means that they pass through the same point. But we haven't done that for medians yet. So today I want to talk about that part, okay? So the theorem tells you that, so if I want to state the theorem, that we want to prove today is that medians of every triangle are concurrent. Yes, so it means that if I draw any arbitrary triangle, and if I draw the medians all pass through the same point. Okay, so let us see why this is the case. Okay, so here, what I do, I draw two medians. For example, the median for side AC and the median for side AB. For drawing the median from this point, I need to find the middle point here. So I call this M. So I know that these two segments are equal in size. And then what I do, I join B to M. This is one of my medians. And I do the same thing here. I find the middle point, probably here, yes. And then I call it N, so I know that this segment is equal to this segment. And I just join N to C, and then to make a new median. They, of course, intersect at a point. The common name for that is to call this G, yes? Okay. And then I want to show that the third median also passes through G. Okay? So if I want to write the proof in detail, so I would say that the medians BM and CN intersect at a point G. We prove that the third median also passes through G. Yes, well, that's the point. But what I can do, I will change the logic a little bit. I would say that I join A to G and continue it. So I will join A to G, okay, and then I continue it. It will intersect this at some point, so let me call it P. I want to show that P is in the middle, is exactly the midpoint. If I can show this, this means that this dotted line is also the median, yes? But I myself drew it from A to G. So this means that this is proven, yes? that understandable? So you want to prove that the third median also passes through G. Instead of proving this, I myself join A to G and extend it, and then I prove that this intersection point is exactly in the middle. So this means that this dotted line in principle is the third median. So my question is that, can I show that BP is equal to PC? Okay, so then you have to write this down. So to show this, to prove this, we join A to G and extend it to intersect the side BC at a point P. We prove that BP is equal to PC. So now my goal is to show that this BP is equal to PC. But the proof is also a little bit convoluted. So then what I do, I will actually extend this a little bit further to get a point A prime, but so that AG is equal to GA prime. Yes. So what I know is that I extend this a little bit more, so that from G to A prime is equal to from A to G. Okay. So we have to write this down when you add something. So we extend GP to A prime, to a point A prime, so that AG is equal to GA prime. So let me put this in a box. This is by construction. So from G to A prime, I know is equal to from A to G by my construction, and then I join A prime to B. We then join A prime to B, for example. So now what happens? We have something like this. Yes? Yeah, it's clear? Okay, now what we know, look at this triangle, A, B, A prime. Yes? Try to not let other things distract you. Forget about this. Just A, B, A prime, this triangle that you see here. This N is the midpoint. Yes, because you see they are equal. And G is also the midpoint from A to A prime because of my construction. AG is equal to GA prime. So G is the midpoint of this side, N is the midpoint of this side, and NG is joining the midpoints of two sides of a triangle. According to one of the versions of midpoint theorem, if you remember, if I have a line segment joining the midpoints of two sides, this segment is parallel to the third side, and the length of that is half of the length of this one. So do you remember that? Yes. So we say that, okay, in triangle A prime B, we know that AN is equal to NB. We also know that AG is equal to GA prime. Yes? So then this means that by midpoint theorem, this means that MNG is parallel to the third side of my triangle, which is BA prime. And we also know that NG is half of this BA prime. Yes. We also have this, actually. Okay, so now let me ask you something. If NG is parallel to BA prime, I hope that you agree with me that GC is also parallel to BA prime. Yes, because GC is just the extension of NG. When this part is parallel to BA prime, definitely the whole line is parallel, and of course GC is also parallel to BA prime. Okay, so from here, now, what we have NG is parallel to BA prime. So from here, I can immediately conclude that GC is also parallel to BA prime. This is something that I will need. So let me call it number 1. Okay, but what I will do more or less the same thing for the other side. So I will join A prime now to C this time and follow more or less the same kind of reasoning, yes? I hope that you agree with me what's going to happen, yes? This time, instead of looking at this triangle, I will look at this triangle, yes? But you see the same thing happens. M is the midpoint and G is also the midpoint. So this line segment joining these two is parallel to this one, and its length is equal to half of that one. So again, I can say that we join A prime to C, and okay, then what we have, in which triangle I am talking, triangle AA prime C this time, I can say that AM is equal to MC. I can say that AG is equal to GA prime. So again, by midpoint theorem, what can I see? I can say that, okay, the same story. GM is parallel to A prime C, and GM is half of A prime C. Okay, but now, so what can I say? I can say that, okay, for the same reason, when GM is parallel to A prime C, GB is also parallel to A prime C, yes? So I would say that GM is parallel to A prime C. This then implies that BG is also parallel to A prime C. Yes? Okay. So this is number 2. But now let us concentrate on this quadrilateral. So you know that the title is quadrilateral, but we are always talking about triangles. The reason is that the proofs that we are presenting are somehow related to the properties of quadrilaterals. So now if you look at this quadrilateral that I am trying to make it clear, it is clear now that this quadrilateral is a parallelogram. Why is that? Because I proved that BG is parallel to A prime C. I also proved that GC is parallel to BA prime. So this is a quadrilateral so that the opposite sides are parallel pairwise, yes? So this means that, so I would say that hence, from number 1 and number 2, I can conclude that B, G, C, A prime is a parallelogram. Parallelogram. Yes? And when it is a parallelogram, what can I conclude from this? What? I know that these are diagonals. Do you agree? So these are diagonals, and then we know that in a parallelogram, the diagonals actually bisect each other. So what I can understand is that, okay, this is equal to that. And of course, I know that this one is also equal to that one. Yes? So this implies that a BP is equal to PC, which I wanted to show. Do you remember? We want to show that BP is equal to PC, so we are done here. And of course, I get something as a byproduct, is that GP is equal to PA prime. Okay? So, concurrency is finished. But there is some very nice property that I want you to know about it. Is there any questions here? Understandable?
Yeah.
Okay. So the point is, what we are supposed to do? We want to prove something very important, which is related to medians. And the point is that, first of all, let me give this a name. There is a name for this center of concurrency for medians. That is called the centroid. Of a triangle. Of the triangle. Or sometimes in physics they call it center of gravity, and that is the reason that we denote it by K. It has a very nice property from physical point of view. If you have a thin, if you have a triangle in the form of a thin metal, and then you find the center of gravity, assuming that this triangle, that metal sheet is actually homogeneous, then if you put the triangle at this point on a needle, it will be on equilibrium. So it will actually be horizontal with the plane. Yes? So because the gravity actually acting here for the triangle. Okay, so that's why we call it the center of gravity in physics, but the mathematics term for that is the centroid. Yes? Okay, and one nice property that you can immediately see is this. AG is always 2 times GP, not only this one, because that is very clear by construction. Is that clear? Mm-hmm. Because we had AG was equal to GA prime by my construction. Do you remember? So we had A, so let me change my color. So AG is equal to GA prime. This means that AG is equal to, instead of GA prime, I can write, now you see on the picture, so this GP and PA prime are the same, so I can write it from GP plus PA prime, but these are the same because this is a parallelogram, yes? So this means that instead of PA prime, I can also write GP, so then it becomes 2GP, yes? So what we get is that AG is 2GP. But let us see the other parts. What about BG and GM? Do you think they will also have the same relation? That BG is also 2 times larger than GM? And the question again for CG and GM. We want to show that yes, this is indeed the case. So that's a very nice property. when you draw the medians, the point of concurrency occurs at a point that actually divides each median to the ratio of 2 to 1. One part is 2 times larger than the other one. But why this is true for the other ones? This is very clear by my construction and because I just showed that this is a parallel. But why BG is 2 times GM?
Couldn't you do the same thing with the quadrilateral for side AC?
Yes, we actually more or less you're right. We need these two parts now. That as a byproduct I got it here. So you see, when this is a parallelogram, it means BG is equal to A prime C. So let me write it here. BG is equal to A prime C because this is a parallelogram. But on the other hand, if you go there and see what we had, okay, I started from here. A prime C is 2 times GM because GM is half of A prime C, so A prime C is 2 times GM. And now instead of A prime C, I can put 2 GM. And this means that BG is equal to 2 GM. Yes? And for the same reason, because again this is a parallelogram, so CG is equal to A prime G. CG is equal to A prime G. A prime B. But if you go back here, we had this one. A prime B divided by 2 is NG, so A prime B is 2 times NG and we are done, yes? So instead of A prime B, I put that, so this becomes GC is equal to 2NG. Okay, so that is also true. So that property is unique to this concurrency point. For the bisectors, for the altitudes, we didn't have that nice property. So if I want to summarize what we get, okay, so what we can do is this. So if I have any triangle, yes, ABC, when you draw the medians, first of all, they are concurrent. So let me change the letters. So usually we call this BM. And then, for example, the middle point here, this is BN. So this means that automatically, if I connect this to this and continue, it will automatically be the median, yes? So this point is called the center of gravity in physics or centroid in mathematics. And then, okay, so this is the picture that you should have in mind. So for example, this length is equal to that length, this one is equal to that one, and this one is equal to this one. I call it P. Okay, so these are the medians, this point of concurrency. And then we need to know that from G to the vertex is 2 times larger from G to the midpoint. And for the same, for the other two as well. So from G to the vertex is 2 times larger from G to the midpoint. And finally, from G to the other vertex is 2 times larger than from G to P. Yes? Okay, so that is something I want you to know here. And more or less we are done with all concurrencies, yes? So this is the concurrency of medians, we have the concurrency of angle bisectors, concurrency of altitudes, and concurrency of side perpendicular bisectors. Okay, now let me, for example, because today I will not teach more, I want to go and solve some of the previous problems left from the previous sessions. So one thing I want you to tell me why this is true, if you have any opinion. So let me just draw any arbitrary triangle here, and then I take the midpoints M, N, and P. So these are midpoints. So this side is equal to this segment is equal to that segment. This is also equal to that, and this is equal to this. And what I do, I join these points to make a new triangle. Now, first of all, I want you to tell me, if you can, why these four triangles are all concurrent. Congruent. All of them are congruent. Why is that the case? For example, let us concentrate on two of them, yes? For example, we want to show that this triangle that in the middle is congruent to this triangle. You can do the same thing and show that this is congruent to this one, and this is congruent to this one, and then of course if this one is congruent to these three, it means all four are congruent. But why, for example, let us concentrate on a pair of them. MNP is congruent to MBP. Why is that?
Because we know that MN is equal to BP.
Why?
Like we did before.
So this is the midpoint theorem, yes? This is the middle point. This is the middle point. I am joining them. So this side is half of BC. Yes? So let me just make it very fast. So AM is equal to MB because that's the midpoint. And for the same reason, AN is equal to NC, that's also the midpoint. But I'm joining the midpoints. By midpoint theorem, I can conclude that MN is half of the third side, which is BC. But on the other hand, if I ask you what is half of BC, you can say BP or equivalently PC. Yes? So instead of half of BC, what I can write that MN is equal to BP. Yes?
And also, they're also parallel.
Yes?
That means the angles are the same angle NMP and angle.
Yes? They're also parallel, so you are using that idea. So that is parallel to that one. And then, okay, then what do you want to say then?
The angle NMP and angle BPM.
NP and M, yes?
They're equal.
They're equal?
Yeah. And MP is common.
Is in common. So this means these two triangles are congruent. Exactly. So you want to tell me also that MN and MN is parallel to BC. So now you say that MN is parallel to BC. What can I do? I can conclude that because these two are parallel and this line is transversal, so this means that I have my Z shape here. So this means this angle, if I call it M1, and this angle, if I call it P1, they are equal. So this means that angle M1 is equal to angle P1. And exactly as you mentioned, this is in common. So I would write that MN is equal to BP, angle M1 is equal to angle P1, and then we also have MP equals to MP. It's common, so I can use the SAS axiom to conclude that this triangle MNP is congruent to the triangle MBP. Yes? And for the same reason, the red one is congruent to this one, the red one is congruent to that one. So I just want you to know that all of them are congruent. Yes? But one thing I want to mention is that what is the relation between the centroid of the big black triangle and the centroid of the smaller red triangle? Centroid is this point. So it means that I am asking you how the point of concurrency of this bigger triangle is related to the point of concurrency of the medians of this red triangle. Do you have any idea?
Is it the same?
Yeah, it seems to be the same, but why do you think they are the same? So the proof is the claim is that we want to say that the centroid of this and the centroid of this coincide.
Oh, is it because the medians of the smaller triangle lie on the medians of the bigger triangle?
Yes, but we need to motivate that. Why is that true? So let us just consider this one. Just if I draw this, if I join this to P, this green line is of course a median of the black triangle. Yes, by definition, this is the midpoint. I am joining them, so this is a median. But the claim is that this one is also a median for this triangle, but of course from this vertex. Yes, from B to, let me call this point, for example, X. Yes. So why that is also true? So I drew this and I want to show that from P to X is also a median for the red one. So this means that I need to convince myself that this one and that one are the same. But they are the same, yes? Because what is this quadrilateral again?
It's a parallelogram.
It's a parallelogram. Why? Because you are joining the midpoints. So this side is parallel to this side. You are joining the midpoints, so this side is parallel to that side. So this is a this is a parallelogram. And these are the diagonals, yes?
Yeah.
And we know that in any parallelogram, the diagonals bisect each other. So this means that this one and that one are the same. Yes? So it means that when I draw a median of the black triangle, that is automatically a median of the red triangle. Yes? So that is the case for the other two medians. The proof is exactly similar. So this means that the centers of gravity of these two triangles are actually the same point. Yes? So that's also good to know. Okay, so there are some problems actually left from the previous sessions. I don't have the complete list in front of me, but let me just recall. So one problem I remember, I talked about that long back, was that I have one triangle. I don't remember how I'll call this, but I just try to give you the idea. So I have a triangle ABC, and then I construct 3 equilateral triangles on each side, but outside the triangle. So what I do, so I would try, so it's hard to draw it very precisely, good shape. So I'm just making a equilateral triangle here. So it means that this length and this length and this length are supposed to be equal. And let me call it C prime here. I do the same thing for the other side. Yeah, so it might be that's not a good picture because it motivates you probably that they are on the same. So this is also this one, and then I do another one, I call this B prime, and then I will do the same thing here. Of course I can show using GeoGebra, but I intentionally, because in the real exam you don't have access to GeoGebra, so you need to understand how to do it by not very precise pictures, okay? So what I'm doing, I'm actually constructing 3 equilateral triangles on each side, but outside of the triangle. Okay, now my question is that we want to show, for example, from A to A prime, if I join A to A prime, I want to show that this line segment is also equal to this line segment, is equal to this line segment. Yes. And this also happens for the third one, but the picture is poor because if I draw it correctly, these 3 orange lines that I am supposed to draw, they will also be concurrent, but the proof of concurrency is hard. Okay? So this is why I want to skip that one, but of course we will study it in 2 or 3 weeks from now. That I was able to prove this using a theorem which is called the Seva theorem. But forget about that. Here, I don't want you to, because I remember when I was teaching this, I asked you to think about if you can prove that they are concurrent. I myself start thinking, but I couldn't find a method that we can immediately use what I have taught so far. I was able to prove the concurrency using Seva theorem that we haven't studied yet. So forget about that part, okay? Or at least if you have an idea, I'm very willing to hear from you as well. So the point is that I want to prove that all these line segments are equal in size, even though when I started from an arbitrary triangle, and these triangles are different in sizes. Okay, so how do you think we can prove that these two, for example, only concentrate on AA prime and BB prime? I want to show that the length of these 2 orange lines are equal. The point, if I want to give you a guide, of course this picture is really poor. This is misguiding a little bit, but that's what it is. My guide for you is to try to show that, let me see if I'm not confused myself now. I want to show that this triangle, if I draw the correct and precise picture, this one, we want to show that this is congruent to this one. Yes. So somehow they share one part in common, but I want to show that these 2 triangles are congruent. If I can show this, hopefully you agree with me, the consequence would be that AA prime is equal to BB prime, yes? If I can show these 2. Okay, but I think it's not hard to see why they are congruent. And you see why?
They have AB in common.
So it might be I am not doing it correctly. So they have AB in common then. Let me see if they are really congruent or not. Or might be I am wrong. This is a very, very poor picture. Might be I am myself confused. So let me see if they are really congruent. No, I think I made a mistake. Are they really congruent? Because, so we know that these sides are all equal, so that somehow should be involved here. So let me see if I have done it right. Let me pause recording to think. Okay, sorry. So I will change my mind. That was not probably correct because I did not have enough information. So I cleaned this. But now let me concentrate here. Yes. And here. So let me name the triangles. A prime, C. This is one of my triangles. So to prevent confusion, let me do not color it, but B prime, C. My claim is to show that they are congruent. Yes? If I can show this, it's a question mark yet, then I am done. But I think it is possible. Now, can you see that? So let us write, to understand this is a little bit messy, to understand this, for this triangle, what are the sides that I have? I have A prime, I have AC, and I have A prime C. Yes? For this triangle, I have BB prime, I have BC, I have B prime C. Yes? These are the sides of that triangle. These are the sides of that triangle. Of course, my goal is to show that these two sides are equal. But I'm claiming that I know that AC is equal to BC. No, AC is equal to B prime C, yes? Do you agree that these two are equal? Because of construction, yes? What is AC? AC is this side of my triangle. And B prime C is this dotted line. But then, do you remember the construction was that this is what? Equilateral. So this means B prime C is equal to AC. So B prime C is equal to AC, we know by construction. Yes? And what about A prime C and BC? A prime C is this dotted line, and BC is one of the sides of my triangle. But again, this is also a equilateral triangle. So by construction, A prime C, by construction, A prime C is equal to BC. Yes? So let me write it a little bit lower. A prime C is equal to BC. But now, either, so I need to give up because I want to prove these two are the same. So I don't know if they are the same or not. So it means that SSS congruency, I need to forget about it because that's my goal. So there are two more left. So, but because I have already two sides, so the good candidate is SAS congruency. So this means that if I can convince myself that the angle between these two are also the same, then I can use SAS axiom and then I can conclude that they are congruent. So now let us not be confused. So what are the angles that I want to convince myself that they are equal? This is AC. So you see this angle, if I can show that this angle is equal to that angle, I am done. Yes? Do you agree? Yeah. Because this is the angle between these two sides. This is the angle between these two sides. If I can show that these two angles are the same, I am done. But this is also clear. Why? Because you see that they share one part in common. So the leftover is this one, the leftover is this one. But these two leftovers are also equal. Yes? Why is that? Because this is a equilateral triangle, so this angle is 60 degrees. So this part is 60 degrees from here to here. And this part is also 60 degrees from here to there.
Yeah.
And then you see that this angle is the same. So the total angle from here to here is 60 degrees plus, let me call this one alpha. The angle from here to here is again 60 degrees plus alpha. So these two angles are the same, whatever alpha is, it doesn't matter. So this means that these two triangles are really congruent based on SAS axiom. And if they are congruent, I can immediately conclude that the third sides are also equal. This means that AA prime is equal to BB prime. Yes, is that understandable? Yes? Okay. So this was one of those problems that we talked about, but I didn't solve it. And then I told you that we will talk about this later, that if I connect C to C prime, of course the proof that the length of that one is equal to the lengths of these two is exactly the same idea. But why this also passes exactly through the intersection point, it needs a little bit more advanced theory in geometry. Okay, any questions? No? Okay, now let us see what was one of the other problems that I didn't solve. So let's pause before. Okay, so for example, if I just draw any kind of a triangle here, I think it's better to get rid of these axes and also grids, yes. Okay, so this is my triangle. Then I want to make an equilateral triangle on each one of these sides, yes? So I think we can do it. We go to regular polygon here, and then we go, hopefully this is the right direction, and then automatically you tell this should be 3. No, it is, so remember I did it in the wrong direction. I need to go anti-clockwise direction. So I go from here to here, and then I ask this one to be 3. So you see it constructs an equilateral triangle on the outside, yes? And then what I do, I will do the same thing here. For that one, I have to go anti-clockwise, and then I will do that 3. Hopefully this also works. That's also an equilateral triangle outside of it. And then I will do the same thing here. So I think I should go in this direction, am I right? 3, otherwise it will jump in, yes. So let me make it a little bit smaller, so here. So that was the situation that we had. So I constructed an equilateral triangle on each side outside of it, yes? And the point is that, the claim is that it doesn't matter with what is ABC, the length of, for example, from B to this is equal to the length from A to E. Yes? So we actually proved that it doesn't matter how this is the case. So of course probably we can also start working around, and I think we should be able to calculate the length by GeoGebra somehow. So let me see if I can do that. The length of this line segment, I will call it what? BF. So this would be the length of the segment, yes, from point to point, B to F. So I would say B to F, yes. And then let me take the copy paste. Can I copy paste or not? This version, you know, this is a little bit strange. I don't know. I can type it again. So the length, yes, of segment. What is the other one? Is AE, yes. A and E, if I have done everything right. So if I calculate the length is 0. So the difference between the length, so you can, I can just get rid of this. So this means that this length, you see, it's 0. So GeoGebra confirms that from A to E is equal to from B to F. And then you see that if I start moving things around, this number 0 is remained fixed here. Yes, so it means that this is always the case, and then we can start playing around to see what happens. But the point is that the third one even is the case. So if I go here and draw the third one, you see it always passes through exactly the same point, which is not trivial. And the proof is, actually I couldn't find a proof based on what we have learned so far, but I was able to prove this using another theorem that we will study. So you see, it doesn't matter how I am just moving them around, they are always concurrent, they are always passing through the same point.
What's the name of that theory?
Pardon?
Theorem.
CEVA. C-E-V-A. Okay. Okay, so that is what we actually learned here, okay? Okay, so another problem was this. Do you remember, this is a little bit more advanced problem, and then we also learned something similar to this. The problem was this. We have a function from the points of the plane to real numbers. So it means that this function f that I have acts on the points on the plane. For example, extend this whiteboard to infinity from all sides, that is your plane. And then you have a function that accepts a point from the plane and gives you a number, a real number back. But this function is like this. F of A plus f of B plus f of C plus f of D is equal to 0 if A, B, C, and D are the vertices of an arbitrary square. Yes? So we just have a function that takes a point from the plane and returns back a number for you, but it also satisfies this very interesting condition that if f acts on the vertices of any square and you add the values, it becomes 0. This is the condition on the function. Now the claim is that this function is a constant function. Okay, so the claim that we want to prove is f is a constant function. Yes, this is the claim. And now, of course, if this is supposed to be a constant function, it means what? It means that f acting on any point, any arbitrary point from the plane, is the same constant number. That is the meaning of being constant. But can you see that what that constant number should be if this problem is correct? If the claim is valid, and this is a constant function, but can you tell me what that constant number is if this theorem is this problem is supposed to be correct? For example, do you think that that constant function point is 5? Do you think that that constant is square root of 2? What that constant should be?
I mean, one answer is 0, isn't it?
Definitely it should be 0. Because if this is going to be constant, that constant appears here, 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 and here. So 4 times that constant is 0, so the constant should be 0. So if the claim in the problem is valid, then we already know what that constant function is. That constant function should be the 0 constant function. But of course, we don't know if this claim is true in the first place, if it is constant. We want to show that, yes, this is a constant function. Okay? So to prove that this is a constant function, it's very interesting. So I would say that let x be an arbitrary point on the plane. We prove that f acting on that x is 0. If I can show this, it means that I proved the claim. But how can I show this? This is very interesting. This point is this, let us consider this to be x. I want to say that f acting on x is equal to 0. But of course, what do I have in my hand? I know only one thing about this function. I know that if this function acts on the vertices of any square, the sum of the values is 0. This is the only assumption that I have. So I have to use this in a very creative way to be able to show that f of x is equal to 0. Because when I start with the point x, I do not have any squares in my hand. So I have to be creative to set up a very nice setting to be able to do that. So one way is to do something like this. I don't know, just draw a line segment so that x is in the middle, exactly, midpoint. So what I do, I draw, for example, you consider a horizontal line here, so that x is the midpoint. And let me call this one, I don't know, m and n. Okay, so what I have done, by construction, mx is equal to xn. That is done by myself. And I do another line perpendicular to this line segment. Okay. But I will not change the length. I want to keep whatever here, and then I will draw this one here. So this means that what I do, I will take this one to be equal to that one as well, and that one. So let me call this one P and Q. Yes? So you have to be patient. This is a little bit a strange way of solving the problem, but I took that x and I just draw a horizontal line with arbitrary length so that x is the middle, and I did the same thing, but I myself made it perpendicular. And now what I do, I don't know, I draw a parallel line from here to here. My point is to construct a lot of squares. That's my goal, yes? And then I draw another one here, and I draw another one here, and I draw another one here. Yes? Is that clear? So I started from that x, I constructed this object, then you see that I have a lot of squares involved, and that's good because I can use this for every 4 points which are sitting as corners of any square. Now let me give them names. So if you don't mind, let me call this A, B, C, and D. Yes? Agree? Now let me start writing this. So do you agree? So I hope that you agree that all of these are squares now based on my construction. The bigger one is also a square. These are very simple things you can prove yourself. But then what I can write that f of x plus f of p plus f of a plus f of m is what? Because these are corners of a square. So if I add these numbers, this number should be definitely 0. If you ask me what are these numbers, I don't know, but I know the sum should be 0 according to the assumption. And I do the same thing here. Yes? So I would say that f of x plus f of n plus f of b plus f of p is equal to 0. Yes? And I do the same thing here. So f of x plus f of n plus f of c plus f of q is equal to 0. And finally, you can guess what I'm going to do. I will write it for the other one. F of x plus f of q plus f of d plus f of m is equal to 0. Yes? So remember, my goal is to show that f of x equals to 0. Do you see what I'm going to do now? Yes? Can you guess? We add them.
Yeah.
All of them.
All of them.
Yes. So this becomes 4f of x. But I want to add them wisely. What do I mean by wisely? Some of them are repeated 2 times. Yes. Which one of them? For example, fp appears here and there. So it is 2. So let me factor a 2 here. and write f of p here because I will have more terms. So you see, first of all, let me just cross them over to make sure that I'm considering everything. I consider 4f of x. I consider 2f of p. And then what I have f of n 2 times. So I would put f of n here. And then what I have f of q 2 times. So I would write f of q, and of course I factored 2 out. And what is left? Okay, I also have f of m 2 times, yes? So I would write f of m. But unfortunately, there are some other terms left, but that's good. You see, f of a, I put them in one pair of brackets. F of a plus f of b plus f of c plus f of d, and the sum of 0 plus 0 plus 0 plus 0, yes? Because I have added all of them. But now what is happening? Can you tell me what is the result here by looking at the picture? 2 times. What is the result here?
0.
It's 0. Why? Because it also constructs another square, yes? I hope that you agree with me. It is not hard to see that this is again another square. Yes? Do you agree? It's very easy to prove that this is a square. And then P, N, Q, and M are the vertices of a square again, and then I'm adding them. So that is definitely 0. Yeah, so this becomes 2 times 0. But what is that sum?
0.
That's also 0. Yes? But then what is the right-hand side? 4 zeros. It is 0. And then what happens? This becomes 4f of x. 0, 0 is equal to 0. And then it means that f of x is indeed equal to 0. So it's a very, very nice problem. We had this problem. This is easier than the one we had before. That was much more, do you remember? I don't know. That was a much harder problem. But this setup was not hard to find. So this means that by this assumption, we can immediately conclude that that function should be a constant function and the value is 0. Yeah, is that understandable? Okay, we have a little bit of time, so I don't remember which problem we can talk about now. Do you remember any problems? Okay, that's also another problem. I already constructed it here. That problem is this. We had, let me clean this one. This is hard to draw for me, but this is why I will construct it using GeoGebra. The problem was this. We have 3 circles with the same radii. They pass through the same point, but of course they also intersect another. So I don't know how to draw them perfectly. So assume that this is a circle. Another circle is passing through this point with the same radius. Okay, so for example, it's hard to draw, but I will show what do I mean by GeoGebra demonstrations. Assume that that is also a circle with the same radius that passes through this fixed point. And I will have another circle that passes through the same fixed point with the same radius. So let me just draw whatever I can here. Something like that. Yes? So this point is fixed, and I have 2 circles with the same radii passing through the fixed point here. And then you will see that I will have more intersection points, 3 more, okay? So I will have 1 intersection point here, and 1 intersection point here, and 1 intersection point here. The claim is that these points also lie on a circle with the same radius. That was the claim of the problem. So we just want to show that if I have 3 circles with the same radii passing through the same fixed point, the other intersection points lie on a circle with the same radius as these. Yeah, so that was the claim in the problem. I think we can actually somehow, I think the picture is not that bad. We can probably work here, because in the exam you don't have access to GeoGebra, so you need to draw some sketching for yourself and be able to prove this. Somehow it's good. So first of all, there is a circle that passes through these 3 points. Why is that?
Because they're the distance from the point to the center point is equal.
No, because we don't know. This is, so why the claim is that, first of all, why do you agree that there is a circle that passes through these 3 points? Because that's not, it's not, by the way, trivial. You can take 3 points. I mean, if I give you 2 points, it is not hard to draw a circle that passes through 2 points. Yes? Why? Because what I do, I draw this line, and I find the middle, draw the perpendicular bisector, put the middle of the compass here, and then open it something. And if I draw the circle, it will also pass through the other point. But if I want to adjust it for 3 points, it is not easy. But we actually proved this in these lessons, yes? Because these are, if I have 3 points, these 3 points always make a triangle for me. And then the center is actually the circumcenter. Do you remember this word?
Yeah.
So that is the circumcenter. If I find the circumcenter, that would be the center of a circle that passes through all the vertices simultaneously. And where the circumcenter is, I need to draw the perpendicular bisector of this, perpendicular bisector of that, and that they will actually go through the same point, and that point is called the circumcenter.
So the centroid and the circumcenter are the same?
No, I don't know. So you see, let me see. The point is that I have this. Yes. I just know, I don't know what is related, but might be you are true, I don't know. If you think that this is the center, we have to convince ourselves. But of course you are right, that is the center. This picture is so poor that even I am confused, Okay? So you are claiming that this fixed point is the circumcenter of this triangle, if that's your claim. Yes? But if that's your claim, you have to prove, you have to bring evidence for that. But I don't know, do you think that this is the case? Do you think that this is the center of that triangle?
I mean, you kind of convinced me that it is the case, but
no, if that is the case, I have, because if this is, so because don't get confused, forget about this picture. If this is the circle,
yeah.
and this is the center, the point is that the distance from the center to the vertices should all be the same, and these are the radii of the circle. But if you are claiming that this is the circumcenter of this triangle, you should convince me that the distance from this to these points are all equal.
Oh, well, that's not the case.
But is it the case?
Not always.
Okay, if that's not always, then it means that we are in trouble, so we cannot claim that, yes? Yeah. Okay, so then what? Okay, so that is a little bit hard. So I would say that let us concentrate on another triangle. Instead of focusing on this triangle, if you want to focus on another triangle, what is your candidate for focusing on another triangle?
A triangle where the 3 vertices are the center points of
centers. Yes. So let us consider this one. So let me consider this center and this center. So let me call them, I don't know, center number 1, center number 2, center number 3. And for the time being, forget about your triangle there and concentrate on this triangle. I don't know if you can visualize it from my picture.
I drew something similar. Yeah.
But the point, this one is now the circumcenter of the green triangle. Yes? So your guess was a little bit close, but it was not for this triangle. I want you to see why do you think that this is the circumcenter of this green triangle, which of course is not our triangle, but we will come to that. Why do you think? It's very, very simple. What is the point? If you want to show that this is a circumcenter, there are two ways. Either you have to convince yourself this is the point of concurrency of perpendicular bisectors, which that's possible in this case, but another one which is simple, draw a line segment from that point to this vertex, to that vertex, and to this vectors, and to this vertex, and claim that, and prove that these are equal in size. But are they?
Yeah.
Why? Because
all the circles have the same.
yes, because I take this one, and I draw this line, I draw that line, and I draw this line. So this one is the radius of this circle, I agree. This one is the radius of that circle, and this is the radius of the other circle. But you remember, the circles have the same radii. So this means that that's proved. So this point, this fixed point, is not the circumcenter of the red one, is the circumcenter of the green one. If I ask you what is the circumradius of this, you would say that this is the same radius, yes? If I ask you, if I draw another circle here, what is the radius of that circle? You will definitely answer the circle of this new one is equal to the radii of the previous ones, yes? This is clear. Is that right? Now, another hard part of this is to prove that this green triangle is congruent to the red one that we already have. If I can prove this, then I am done. Because if two triangles are congruent, the circle of them have the same radii. And then we are done. Yes? I don't think we can finalize this today, but that's a good point. And now you have a hint. So the only thing that you need to prove is to prove that this red triangle is congruent to the green triangle. But I want to make sure, if you prove this, this is done. Do you agree? Because if two triangles are congruent, the circumradius of the circles are also equal. And then we are done. Yes? So now you have this hint. I will next time I will start from here, and then we continue our lesson. Any questions? Thank you.
Thank you.